Hello and welcome to the Sleepy Physicist. I'm so glad you're here, whether you're settling in for the night, curling up with a warm drink, or simply seeking a moment of cosmic wonder to ease your mind. Tonight, we're embarking on a gentle journey to one of the most perplexing mysteries that has ever emerged from the depths of space, a discovery so profound and so utterly bewildering that it's forcing scientists to question everything we thought we knew about the universe itself. Picture this for a moment. You're an astronomer, peering deeper into space than any human has ever looked before, expecting to see the faint, predictable glow of ancient galaxies forming in the cosmic dawn. Instead, you discover something that simply shouldn't exist. 300 impossibly bright objects blazing with the fury of 1,000 suns, existing at a time when the universe was supposedly too young and too sparse to create such magnificent beacons. And stranger still, scattered among them are tiny crimson dots, no bigger than cosmic breadcrumbs, yet harbouring black holes so massive they defy every law of physics we've spent centuries establishing. This isn't science fiction. This is the reality that the James Webb Space Telescope has unveiled, and tonight we're going to explore these cosmic anomalies together, slowly and thoughtfully, allowing the profound implications to settle like stardust on our understanding of existence itself. Before we begin this cosmic meditation, if you find comfort in these slow journeys through the mysteries of science, I'd be deeply grateful if you tap the like button and subscribe to join our community of curious minds. And I'm always fascinated to know where in the world you're watching from and what time it is in your corner of the universe. Feel free to share in the comments, whether it's midnight in Mumbai or dawn breaking over Denver. Now, take a deep breath and let your mind drift outward, past the familiar glow of our sun, beyond the comfortable boundaries of our solar system, and into the vast cathedral of space where the James Webb Space Telescope keeps its silent vigil. To understand why these discoveries are so revolutionary, we first need to appreciate what makes the James Webb Space Telescope such an extraordinary achievement. Imagine, if you will, a mirror nearly 7 meters across, larger than most living rooms, delicately unfolded in the darkness of space, like a technological flower blooming in the cosmic void. This magnificent instrument doesn't just observe space, it observes time itself, peering backward through the universe's history with a clarity that would have seemed magical to astronomers just decades ago. The telescope sits in a gravitational sweet spot, about 1.5 million kilometers from Earth, at what scientists call the second Lagrange point. Here, in this cosmic balance point between the gravitational pulls of Earth and Sun, Webb maintains its position with minimal effort, like a surfer riding an invisible wave of space-time. Protected by a sun shield the size of a tennis court, the telescope's instruments remain colder than the surface of Pluto, allowing them to detect the faintest whispers of infrared light from the most distant reaches of the universe. But why infrared light, you might wonder? It's a beautiful consequence of cosmic expansion itself. When the universe stretches the fabric of space, it stretches the wavelengths of light travelling through it, like pulling on a spring until its coils spread apart. Light that was once visible becomes infrared, and light that was once ultraviolet becomes visible. This phenomenon, called redshift, means that the most ancient light in the universe reaches us not as the brilliant blue and white glow it once was, but as the deep or warm radiation that only infrared eyes can see. Webb's instruments are so sensitive they could detect the heat signature of a candle on the moon, or distinguish between the infrared glow of different molecules in the atmosphere of a planet orbiting a distant star. But perhaps most remarkably, They can peer back through cosmic time itself, observing galaxies as they appeared when the universe was just a small fraction of its current age. When we look at a star 10 light years away, we see it as it was 10 years ago. When Webb looks at objects 13 billion light years distant, it sees them as they existed 13 billion years ago, when the universe was young and strange and governed by rules we're only beginning to understand. In essence, Webb is the ultimate time machine, not travelling through time, but collecting ancient light that has been journeying toward us since before our sun existed, before our galaxy took its current shape, before the very concept of planets like Earth had meaning. Now imagine you're part of a research team at the University of Missouri, spending months carefully analysing Webb's deepest images of the early universe. You're expecting to see faint, primitive galaxies, the cosmic equivalent of flickering candles in vast darkness. The theoretical models predict these early galaxies should be small, dim, and sparse, like scattered embers from the universe's first fires. Instead, your screens light up with something unprecedented. 300 objects blazing with impossible brilliance, shining like cosmic lighthouses in an era when the universe should barely have had the materials to light a match. These aren't just slightly brighter than expected, they're so luminous they violate our most fundamental understanding of how galaxies form and evolve. Think of it this way. Imagine you're studying the history of human civilization, and you expect to find simple stone tools from our earliest ancestors. Instead, you discover 300 fully modern cities, complete with skyscrapers and electric lights, existing at a time when humanity had supposedly just learned to control fire. That's the level of cosmic confusion these objects represent. According to our best models of cosmic evolution, built on decades of observations and refined through countless computer simulations, early galaxies should be constrained by the simple mathematics of time and growth. Stars form from gas clouds, but this process takes time. Massive stars live fast and die young, but their life cycles still span millions of years. Galaxies grow by merging with smaller neighbours and accumulating matter from their surroundings. But this cosmic construction project should unfold over hundreds of millions of years. These bright objects seem to mock such leisurely timescales. They appear to have assembled massive stellar populations, accumulated enormous amounts of matter, and begun shining with the intensity of mature galactic systems in what should have been insufficient time. It's as if the universe's early chapters were written in fast forward, with cosmic evolution proceeding at a pace that our physics struggles to explain. The implications ripple outward, like waves in a cosmic pond. If galaxies could form this quickly and grow this massive in the early universe, what does that say about the nature of dark matter, the invisible scaffolding that shapes cosmic structure? What does it tell us about the first generation of stars, those massive, short-lived beacons how does it change our understanding of when and how the universe transjured the heavier elements needed for planets and life, issued from a dark, empty void to a cosmos rich with light and structure? These questions don't have easy answers, and perhaps that's part of their beauty. Science progresses not just through confirming our expectations, but through moments of profound surprise when the universe reveals aspects of itself that force us to expand our imagination and refine our understanding of reality. But if those impossibly bright early galaxies weren't puzzling enough, Webb had an even stranger surprise waiting in its data. Scattered throughout these ancient images were tiny red specks, so small they could easily be overlooked, yet so mysterious they've become known simply as little red dots, or LRDs, in the understated language of astronomy. Picture these objects in your mind. Each one is incredibly compact, typically no more than 2% the radius of our Milky Way galaxy. Many are even smaller, with radii of just 150 light-years, making them cosmic pinpricks in the vastness of space. To put this in perspective, if our galaxy were the size of North America, these little red dots would be no bigger than a small city. Yet within these minuscule volumes, something extraordinary and impossible appears to be happening. The first hint of their strangeness comes from their colour. While most early galaxies appear blue or white from the light of young hot stars, these objects glow with a distinctive reddish hue. This crimson signature initially suggested they might be older, more mature systems, their light dominated by cooler, redder stars. But as astronomers dug deeper into their properties, a more bewildering picture emerged. Using spectroscopy, the technique of splitting light into its component colours like a prism creating a rainbow, researchers discovered that these little red dots contain gas moving at absolutely staggering velocities. We're talking about material whipping around at nearly 2 million miles per hour. Speeds so extreme, they can only be explained by the presence of supermassive black holes with gravitational fields intense enough to accelerate matter to such incredible velocities. But here's where the mystery deepens into something almost surreal. According to the well-established relationships between galaxies and their central black holes, observed consistently throughout the nearby universe, a galaxy's central black hole typically contains about 1/10% of the galaxy's total stellar mass. It's a cosmic proportion that seems to hold true across billions of years of cosmic history, from small dwarf galaxies to massive elliptical systems. The little red dots obliterate this relationship. If these objects truly harbour the supermassive black holes their gas velocities suggest, these black holes would account for up to 40% of their host galaxy's mass. Imagine a situation where your heart weighed nearly half as much as your entire body, and you'll begin to appreciate how fundamentally this violates everything we understand about cosmic proportions. This isn't just a minor discrepancy or a small adjustment to our models. It's a complete overturning of one of the most reliable relationships in astrophysics. Like discovering that some trees grow roots that are 10 times heavier than their trunks and branches combined. It forces us to question whether these objects represent an entirely unknown phase of cosmic evolution, or whether our understanding of how black holes form and grow is fundamentally incomplete. As if the little red dots weren't mysterious enough, they harbour yet another puzzle that has left astronomers genuinely perplexed. When supermassive black holes actively feed on surrounding matter, they should blaze like cosmic beacons across multiple wavelengths of light. The process of matter spiralling into a black hole, heating to millions of degrees as it accelerates toward the event horizon, should produce copious amounts of high-energy X-ray radiation. It's one of the most reliable signatures of active black holes throughout the universe. Yet when astronomers turned X-ray telescopes toward these little red dots, they found something deeply unsettling: silence. Most of these objects, despite showing every other sign of harbouring actively feeding supermassive black holes, produce no detectable X-ray emission whatsoever. It's like watching someone vigorously stir a pot of soup while producing no sound, no steam, and no aroma. This X-ray paradox has forced scientists to consider possibilities that stretch the boundaries of known physics. Perhaps these black holes are surrounded by such dense shrouds of gas and dust that all X-ray radiation is completely absorbed before it can escape. Imagine trying to see the light from a candle buried deep inside a thick, heavy blanket. and you'll get a sense of how thorough this obscuration would need to be. Alternatively, these black holes might be feeding through mechanisms we've never observed before, somehow converting matter to energy through processes that don't produce the expected X-ray signatures. Or perhaps we're witnessing a transitional phase in black hole evolution that occurs only under the extreme conditions of the early universe, a cosmic adolescence that no longer exists in today's mature cosmos. Each potential explanation raises as many questions as it answers, and the scientific community remains genuinely divided about what these objects represent. In a field where astronomers can typically provide reasonably confident explanations for most cosmic phenomena, the little red dots stand out as genuine mysteries, objects that have left experts saying, quite literally, we don't really know what they are. Perhaps the most haunting aspect of the little red dot mystery is their apparent disappearance from cosmic history. These enigmatic objects seem to have blazed into existence around 600 million years after the Big Bang, dominated their cosmic epoch for perhaps 1 billion years, and then simply vanished. When astronomers survey the modern universe, they find no clear counterparts to these ancient red enigmas. It's as if an entire civilization of cosmic objects lived, thrived, and disappeared before the universe reached its 2nd billion birthday, leaving behind only the fading light that Webb's instruments can detect across the vast reaches of space and time. This temporal mystery adds another layer to their enigmatic nature. What happened to them? Did they evolve into something else, merge with larger systems, or simply burn out like cosmic fireworks that blazed brilliantly and then faded into darkness? The leading theory suggests they may have been victims of their own success, growing so rapidly and burning so brightly that they quickly exhausted their fuel supplies or disrupted their own formation processes. As the universe aged and its overall density decreased, the extreme conditions that allowed these objects to form may have simply ceased to exist, closing a unique chapter in cosmic evolution that can never be repeated. This temporal aspect of the mystery reminds us that the universe has not always been as it is today. Just as Earth's history includes epochs dominated by creatures and environments that no longer exist, cosmic history may include phases of galaxy formation and black hole growth that were possible only under the universe. The little red dots may special conditions of the young represent cosmic dinosaurs, magnificent and powerful creatures of their time, but ultimately unable to survive in the changing environment of an evolving cosmos. As we pause here in our journey through these cosmic mysteries, take a moment to contemplate the profound strangeness of what Webb has revealed. In just a few years of operation, this remarkable telescope has uncovered objects that challenge our most fundamental assumptions about how the universe works, reminding us that despite centuries of scientific progress, the cosmos still holds secrets that can surprise and humble us. There's so much more to explore in this cosmic detective story, from the theoretical frameworks scientists are developing to explain these anomalies, to the revolutionary discoveries Webb is making about the very first galaxies and black holes in cosmic history. In our next exploration, we'll delve deeper into the cutting-edge theories attempting to solve these puzzles and examine how these discoveries might reshape our understanding of reality itself, including the mind-bending possibility that the universe might actually be two-dimensional. But that's a journey for another time, when we can settle in together once more to explore the beautiful mysteries that surround us in this vast, wonderful, and endlessly surprising cosmos. In the quiet depths of theoretical physics, where mathematics meets imagination, scientists are beginning to piece together a possible explanation for these cosmic enigmas, and it involves one of the universe's most mysterious components, dark matter. This invisible substance, which outweighs all visible matter by a factor of 5 to 1, forms the hidden skeleton upon which the entire cosmic web is built. Yet like a master sculptor working in shadows, dark matter shapes everything we see while remaining forever beyond our direct perception. Picture dark matter halos as cosmic cradles, vast gravitational wells that collect and nurture the formation of galaxies. Most of these halos spin, rotating slowly through the eons like massive celestial pinwheels. But what if some halos barely spin at all? What if, in the early universe, there existed rare pockets of dark matter that rotated so slowly they were almost perfectly still? This is where the story becomes truly fascinating. When a typical spinning dark matter halo begins to collect gas and form stars, that rotation spreads matter outward, creating the familiar disk-like structures we see in spiral galaxies like our own Milky Way. But a halo with virtually no spin would have no such centrifugal force to spread matter outward. Instead, gravity would pull everything inward with relentless efficiency, compressing gas, stars, and forming black holes into incredibly dense, compact structures. Imagine trying to pack a suitcase while spinning around versus packing it while standing perfectly still. The spinning motion would scatter your belongings everywhere, making it difficult to fit everything in efficiently. But standing still, you could compress and organize everything into the smallest possible space. This is essentially what researchers believe happened with the little red dots. They formed in cosmic environments that were unusually calm and still, allowing matter to be packed together with extraordinary density. This theory, published in the astrophysical journal Letters, suggests that these mysterious objects represent a brief but crucial phase in cosmic evolution, when the conditions were just right for this extreme type of galaxy formation. As the universe aged and evolved, these special low-spin environments became increasingly rare, which would explain why we don't see little red dots forming in the modern cosmos. But there's something almost poetic about this explanation. In a universe that's constantly in motion, constantly spinning and swirling and dancing through space, the most extraordinary objects may have formed in pockets of perfect stillness. It's a reminder that sometimes, in both cosmic and human scales, the most profound transformations happen not in chaos or violent motion, but in moments of deep, concentrated calm. As we drift deeper into this cosmic mystery, we encounter something that challenges one of our most fundamental assumptions about time itself, at least on cosmic scales. We've grown comfortable with the idea that the universe is patient, that cosmic processes unfold over billions of years with the steady persistence of geological time. Star formation, galaxy growth, black hole evolution, all of these seem to follow predictable schedules written in the language of physics and chemistry. The objects Webb has discovered suggest that the early universe operated on an entirely different timeline. Consider the galaxy JD's GS-C4, spotted by Webb existing just 290 million years after the Big Bang. In cosmic terms, this is like finding a fully grown oak tree in a forest that was planted just last week. The galaxy is not only surprisingly massive and mature, but it's actively forming stars and has already assembled the complex structures we typically associate with much older galactic systems. This discovery forces us to confront an uncomfortable possibility. Perhaps our models of cosmic evolution are missing something fundamental. Maybe the early universe had access to processes or mechanisms that simply don't exist today, like a cosmic cookbook with recipes that only worked when the ingredients of space and time had different properties than they do now. Think about it this way. The universe in its first few 100 million years was denser, hotter, and more chaotic than anything we observe today. Gas clouds could collide and merge with tremendous efficiency. The first generation of stars, massive beyond anything that forms in the modern universe, lived fast and died young, enriching their surroundings with heavy elements in cosmic eye blinks. Perhaps under these extreme conditions, the normal bottlenecks that limit galaxy formation simply didn't exist. It's a bit like the difference between trying to build a city in the modern world with all its regulations, environmental concerns, and complex logistics, versus building in a frontier environment where resources are abundant and there are no rules to slow you down. The early universe may have been cosmic frontier territory, where galaxies could grow with a speed and efficiency that seems impossible by today's standards. Webb's observations suggest that the first billion years of cosmic history were far more eventful and transformative than we ever imagined. Instead of a slow, gradual awakening from the cosmic dark ages, we may be seeing evidence of a rapid, explosive period of structure formation that set the stage for everything that followed. Perhaps nowhere is this accelerated timeline more puzzling than in the realm of supermassive black holes. These cosmic giants, millions or billions of times more massive than our Sun, sit at the hearts of nearly every large galaxy in the universe. For decades, astronomers have assumed they grew through a relatively straightforward process, starting as smaller black holes formed from the collapse of massive stars, then slowly accumulating mass over cosmic time by consuming surrounding matter and merging with other black holes. This gradual growth model made sense because there are fundamental limits to how quickly black holes can grow. When matter falls into a black hole, it heats up and begins to glow intensely, creating radiation pressure that pushes against additional infalling material. This creates what's known as the Eddington limit, a natural speed limit for black hole growth that prevents them from consuming matter faster than a certain rate. Yet Webb has discovered supermassive black holes in galaxies so young that there simply hasn't been enough time for them to grow through conventional mechanisms. It's like finding a massive, ancient tree in a forest that was planted just yesterday. The math simply doesn't add up using our current understanding of black hole physics. The discovery of these impossibly early supermassive black holes has forced astronomers to consider exotic possibilities. Perhaps some black holes formed not through stellar collapse, but through the direct gravitational collapse of massive gas clouds in the early universe. Imagine a cloud of primordial gas so large and dense that it skipped the star formation phase entirely and collapsed directly into a black hole. These direct collapse black holes could start their lives already weighing hundreds of thousands of solar masses, giving them a significant head start in the cosmic growth race. Alternatively, maybe the Eddington limit wasn't as restrictive in the early universe. Perhaps the different conditions of the young cosmos allowed black holes to grow much faster than the theoretical maximum we observe today. Some theories suggest that in the dense, gas-rich environment of the early universe, black holes could have grown through super Eddington accretion, consuming matter at rates far beyond what seems possible in the modern cosmos. There's something almost magical about these possibilities. They suggest that the early universe was not just younger and denser than today's cosmos, but operated according to different rules entirely. Like a cosmic childhood, where the laws of physics were more flexible, allowing for rapid growth and dramatic transformations that become impossible as the universe matured. As we continue our gentle exploration of these cosmic mysteries, let's turn our attention to the environment in which these impossible objects formed. The early universe was a very different place than the cosmos we observe today, and understanding these differences is crucial to appreciating why Webb's discoveries are so revolutionary. Imagine the universe when it was just a few 100 million years old, roughly 2% of its current age. The cosmic web, that vast network of dark matter filaments that gives structure to the universe, was still taking shape. Gas densities were much higher than they are today, and the spaces between forming galaxies were filled with pristine hydrogen and helium, the primordial elements forged in the Big Bang itself. This was a universe without heavy elements, at least initially. There were no carbon atoms, no oxygen, no silicon or iron. The first stars that formed in this environment were unlike anything we see today. They were massive beyond our current experience, sometimes hundreds of times more massive than our Sun, burning with incredible intensity and living spectacularly brief lives measured in mere millions of years, rather than the billions of years that smaller stars like our Sun can sustain. When these first-generation stars died, they did so in explosions of unimaginable violence, supernovas and hypernovas that enriched their surroundings with the heavy elements necessary for planets, life, and more complex stellar chemistry. But this process of cosmic enrichment was patchy and uneven. Some regions of the early universe received heavy doses of these newly forged elements, while others remained relatively pristine. The little red dots and impossibly bright early galaxies may have formed in these specially enriched environments, cosmic oases, where the conditions were just right for rapid, efficient structure formation. Picture these regions as stellar nurseries operating under completely different rules than anything we see in the modern universe, where gas could cool and collapse with extraordinary efficiency, and where the feedback processes that normally regulate star formation were either absent or operating in entirely different ways. It's a bit like comparing modern agriculture, with its careful soil management and regulated growing conditions, to the explosive fertility of a newly formed volcanic island, where life can colonize and flourish with remarkable speed in the mineral-rich soil. The early universe may have contained cosmic equivalents of these volcanic islands, special environments where galaxies could grow with a speed and intensity that seems impossible by today's standards. One of the most haunting aspects of the little red dots is their apparent disappearance from the cosmic stage. These objects blazed into existence during a relatively brief window of cosmic history, roughly between 600 million and 1.5 billion years after the Big Bang, and then seemingly vanished without a trace. It's as if an entire category of cosmic objects lived, thrived, and went extinct, leaving behind only the ancient light that Webb can detect across the vast gulfs of space and time. This temporal mystery adds a profound layer to our cosmic detective story. What happened to these enigmatic objects? Did they evolve into something else, merge with larger systems, or simply burn out like cosmic fireworks that blazed brilliantly and then faded into darkness? The leading theory involves what astronomers call inside-out growth. As the universe aged and expanded, the overall density of gas and dark matter decreased. The extreme conditions that allowed little red dots to form their incredibly compact, dense structures may have gradually disappeared. As these objects continue to evolve, they may have begun to grow outward, adding new stars in their outer regions, while their central black holes became less active due to the decreasing supply of nearby gas. This evolutionary process would have gradually transformed the little red dots from compact red objects dominated by their central black holes into larger, bluer galaxies, more similar to what we see in the modern universe. It's a bit like watching a time-lapse video of a flower blooming, where the tight closed bud gradually opens into a larger, more spread out bloom. This transformation hypothesis is supported by the timing of the little red dot's disappearance, which coincides with several major transitions in cosmic history. Around 1.5 billion years after the Big Bang, the universe underwent what's known as the end of the epoch of reionization, a period when the first stars and galaxies pumped enough energy into the cosmos to fundamentally change the properties of intergalactic gas. This cosmic phase transition may have been the death knell for little red dot formation. The changed conditions in the universe may have made it impossible for new objects of this type to form, while causing existing ones to evolve into more conventional galaxy types. It's a reminder that the universe has not always been as it is today, and that cosmic evolution includes chapters that can never be repeated. While we've been focusing on the grand mysteries of galaxy formation and black hole evolution, Webb's discoveries have equally profound implications for the cosmic chemistry that makes life possible. The telescope's ability to peer into the heart of star-forming regions has revealed complex organic molecules swirling around infant stars, the same chemical building blocks that would eventually make their way to planets like Earth. These observations around protostars, stellar nurseries similar to what our own sun would have been 4.6 billion years ago, show that the ingredients for life are not rare accidents but common outcomes of the star formation process. Webb has detected everything from simple compounds to complex molecules, including ethanol and organic acids, the same substances that played crucial roles in the chemistry of early Earth. This discovery has a beautiful symmetry with our exploration of the early universe's mysterious objects. While we're puzzling over galaxies and black holes that seem to violate the normal rules of cosmic evolution, we're simultaneously discovering that the chemical foundations for life appear to be universal and abundant throughout the cosmos. It's as if the universe, even in its most mysterious and rule-breaking phases, has always been preparing the stage for complexity, chemistry, and perhaps ultimately consciousness. The presence of these organic molecules around forming stars suggests that planetary systems throughout the universe may have access to the same chemical toolkit that enabled life on Earth. Every star system may be seeded with the molecular building blocks necessary for the kind of complex chemistry that leads to biology. It's a humbling and inspiring thought that connects our local story of life on Earth to the grand narrative of cosmic evolution. This chemical abundance also adds another layer to our appreciation of the early universe's mysteries. The same epoch that produced impossible galaxies and mysterious little red dots was also the time when the universe first began creating the heavy elements and complex molecules that would eventually make planets, chemistry, and life possible. It's as if the cosmos was simultaneously writing the rules for large-scale structure formation and fine-tuning the chemical recipes that would billions of years later enable beings like us to contemplate these very mysteries. As our cosmic journey continues, Webb has provided us with an unexpected gift: the opportunity to study material from other star systems directly. The interstellar comet 3I Atlas, racing through our solar system at record-breaking speeds, carries within its icy nucleus a chemical fingerprint from its home among distant stars. Webb's observations revealed that this cosmic visitor has an unusually high carbon dioxide to water ratio, suggesting it formed in an environment very different from the region where our own solar system condensed. The comet's extreme velocity, the highest ever recorded for a visitor to our solar system, tells the story of a billions-year journey through interstellar space, gaining momentum from gravitational encounters with stars and stellar remnants along the way. There's something deeply moving about this interstellar messenger. Here is an object that formed around another star in another part of our galaxy, under conditions we can only guess at. It has been wandering the cosmic wilderness for eons, carrying within its frozen depths the chemical signature of its distant birthplace. And now, through the patient work of astronomers and the remarkable capabilities of Webb, we can study this alien chemistry directly. The unusual composition of 3I Atlas suggests that planetary formation processes throughout the galaxy are more diverse than we might have expected. Just as Webb has shown us that galaxy formation in the early universe followed different rules than we anticipated, this interstellar visitor reminds us that star and planet formation in different regions of our galaxy may also follow different pathways, creating diverse families of worlds with their own unique chemical characteristics. In a sense, every interstellar object that visits our solar system is like receiving a postcard from another part of the galaxy, carrying news about conditions and processes in stellar neighborhoods we may never be able to visit directly. These cosmic messengers expand our understanding of the galactic environment and remind us that our solar system is just one example among billions of possible planetary arrangements. As we near the end of our gentle exploration of these cosmic mysteries, it's worth reflecting on what these discoveries tell us about the nature of scientific understanding itself. Webb's revelations remind us that despite centuries of progress in astronomy and physics, the universe still holds surprises that can fundamentally challenge our assumptions about how reality works. The scientific method thrives on these moments of surprise and confusion. When observations don't match our predictions, it's not a failure of science, but an opportunity for growth. The impossible galaxies, mysterious little red dots, and unexplained black holes that Webb has discovered are invitations to expand our understanding, to develop new theories, and to imagine possibilities we hadn't previously considered. This is how knowledge advances, not through the gradual accumulation of expected results, but through paradigm-shifting discoveries that force us to see the universe with fresh eyes. The history of science is filled with moments when new observations overturned established ideas. When Galileo's telescope revealed moons around Jupiter, when Edwin Hubble discovered the expansion of the universe, when the cosmic microwave background confirmed the Big Bang theory. Webb's discoveries represent the latest chapter in this ongoing story of cosmic revelation. Each impossible object, each mysterious phenomenon, each violation of our expectations brings us closer to a deeper understanding of how the universe actually works, rather than how we assumed it worked. And perhaps that's the most beautiful aspect of these cosmic mysteries. They remind us that we live in a universe far stranger, more wonderful, and more surprising than our current theories suggest. They invite us to remain humble before the vastness of the unknown, while simultaneously inspiring us to push the boundaries of human knowledge ever further into the cosmic frontier. As you settle into sleep tonight, or continue with your day wherever you are in the world, carry with you this sense of cosmic wonder. We are part of a universe that still holds profound mysteries, a cosmos that continues to surprise and delight us with its endless creativity and complexity. And through instruments like Webb, we have the privilege of glimpsing these cosmic secrets, one photon of ancient light at a time. The universe is vast, mysterious, and endlessly fascinating. And we're only just beginning to understand its true nature. In our next journey together, we'll explore one of the most mind-bending possibilities emerging from modern physics. The idea that our three-dimensional reality might actually be a projection from a two-dimensional surface, a cosmic hologram that challenges everything we think we know about the nature of space, time, and reality itself. Until then, sleep well, dream of distant galaxies, and remember that in this vast cosmic story, you're both observer and participant in one of the greatest adventures ever undertaken. As we venture deeper into these cosmic puzzles, we encounter perhaps the most mind-bending possibility of all, one that emerges not from the distant galaxies Webb observes, but from the intersection of quantum mechanics and general relativity here in our own theoretical laboratories. It's a concept so counterintuitive that even physicists who work with it daily sometimes pause in quiet amazement at its implications. Imagine for a moment that everything you perceive as three-dimensional reality, every depth and shadow and sense of space around you, is actually information encoded on a two-dimensional surface, like a cosmic hologram projected from the edges of the universe itself. This isn't science fiction speculation. It's a serious theoretical framework that some of the world's leading physicists believe might explain not just the mysteries Webb has discovered, but the fundamental nature of reality itself. The holographic principle suggests that all the information contained within a volume of space can be represented as data stored on its boundary, much like how a hologram on a credit card contains a three-dimensional image encoded in a flat surface. Applied to cosmology, this means that our entire observable universe, with all its galaxies, stars, planets, and the mysterious objects Webb has revealed, might be information patterns dancing on a distant two-dimensional screen. This remarkable idea emerged from studies of black holes, those cosmic enigmas that seem to be central to so many of Webb's puzzling discoveries. When physicists tried to understand how information behaves when it falls into a black hole, they discovered that the black hole's entropy, its measure of information content, depends not on its volume, but on the area of its surface. It's as if the black hole's three-dimensional interior is somehow encoded in the patterns on its two-dimensional boundary. Stephen Hawking once described this realization as one of the most surprising discoveries in theoretical physics, comparing it to discovering that a library's entire collection of books could be perfectly represented by the patterns of dust on its walls. The implications ripple outward, like waves in the fabric of understanding itself, suggesting that space and time, as we experience them, might be emergent properties of more fundamental information patterns. If this seems impossibly abstract, consider how it might relate to the cosmic mysteries we've been exploring. The little red dots with their impossible black hole masses, the impossibly bright early galaxies, the rapid pace of early cosmic evolution, all of these anomalies might make more sense if space-time itself has different properties than we've assumed. If reality is holographic, then the rules governing how matter and energy behave might be more flexible than our three-dimensional intuition suggest. There's another layer to this theoretical tapestry that connects our cosmic mysteries to the strange world of quantum mechanics. Deep in the realm of the very small, particles can become entangled, sharing information instantaneously across vast distances in ways that Einstein famously called spooky action at a distance. This quantum entanglement, once dismissed as a curious laboratory phenomenon, may actually be one of the fundamental mechanisms by which the universe constructs itself. Recent theoretical work suggests that the fabric of space-time itself might be woven from quantum entanglement, like a cosmic tapestry where each thread connects distant regions of the universe in patterns too complex for our classical minds to fully grasp. If this is true, then the extreme objects Webb has discovered might represent regions where this quantum fabric behaves in unusual ways, creating pockets of space-time with properties dramatically different from what we observe in our local cosmic neighbourhood. Picture the universe as a vast ocean of quantum information, with waves and currents of entanglement flowing between distant regions. In most areas, these currents flow smoothly, creating the stable, predictable space-time we experience in our daily lives. But in the early universe, when everything was denser and more chaotic, these quantum currents might have created turbulent eddies and whirlpools, regions where the normal rules of physics were stretched, bent, or temporarily suspended. The little red dots and their impossible black holes might be fossil remnants of these quantum storms, objects that formed when the information theoretic structure of space-time itself was still settling into its current patterns. Their seemingly impossible properties might not violate the laws of physics so much as reveal laws we haven't discovered yet, principles that govern how quantum information organizes itself into the illusion of three-dimensional reality. This perspective transforms our cosmic detective story from a tale of mysterious objects to a deeper investigation into the nature of existence itself. Each anomaly Webb discovers becomes a clue not just about galaxy formation or black hole physics, but about the fundamental architecture of reality, the hidden scaffolding upon which our entire experience of being is constructed. As we drift further into these theoretical waters, we encounter one of the most profound puzzles in modern physics, the information paradox. It's a question that connects the microscopic world of quantum mechanics to the cosmic scale mysteries Webb has revealed, and it asks something deceptively simple yet deeply unsettling about the nature of reality itself. The paradox arises when we consider what happens to information when it falls into a black hole. According to quantum mechanics, information can never be truly destroyed. It can only be transformed or hidden. But according to general relativity, anything that falls into a black hole disappears forever when the black hole eventually evaporates through Hawking radiation. These two fundamental theories of physics seem to contradict each other at the most basic level, creating a puzzle that has occupied the greatest minds in theoretical physics for decades. The resolution to this paradox might hold the key to understanding not just black holes, but the entire structure of cosmic evolution. If information is truly preserved in black holes, then every particle, every quantum state, every pattern of matter and energy that has ever fallen into these cosmic giants throughout the universe's history is somehow encoded in their structure. Black holes become not destroyers of information, but cosmic libraries, repositories of everything that has ever been. This has profound implications for the mysterious objects Webb has discovered. The supermassive black holes in the little red dots, with their impossible masses and strange behaviours, might not just be gravitational anomalies, they might be information processing systems of unimaginable complexity, quantum computers that encode and manipulate the data patterns from which reality itself emerges. Consider the possibility that consciousness, life, and intelligence are not accidents that occasionally emerge from dead matter, but inevitable consequences of the universe's information processing capabilities. If black holes are indeed cosmic libraries, and if the universe is fundamentally made of information rather than matter and energy, then the appearance of minds capable of understanding these mysteries might be not a lucky coincidence, but a natural outcome of the cosmos coming to know itself. In this view, our efforts to understand the universe through instruments like Webb become part of a larger story, the universe's own journey towards self-awareness. Every photon of ancient light we collect, every pattern we recognize in the cosmic data, every theory we develop to explain these mysteries contributes to the cosmos's growing understanding of its own nature. The anomalies Webb has discovered might also connect to one of the most speculative yet compelling ideas in modern cosmology: the possibility that our universe is just one bubble in an infinite sea of universes, each with its own physical laws, constants, and evolutionary history. This multiverse hypothesis, once relegated to the realm of science fiction, has gained serious theoretical support as physicists have grappled with the fine-tuning problems that make our universe so remarkably suitable for the existence of stars, planets, and life. If the multiverse is real, then the strange objects Webb has found might represent regions where the boundary between universes becomes thin, places where the physical constants that govern reality subtly shift or blend. The impossibly massive black holes in little red dots might be artifacts of interactions with neighbouring universe bubbles, cosmic border zones, where different sets of physical laws meet and create hybrid phenomena that neither universe could produce on its own. This possibility adds yet another layer of mystery to our cosmic detective story. Instead of simply trying to understand how unusual objects form within our own universe, we might be glimpsing evidence of a much larger reality, a multiverse where billions or trillions of different universes evolve according to their own unique rules and histories. The implications are staggering. If our observations of impossible cosmic objects are actually glimpses of multiverse interactions, then every anomaly Webb discovers becomes a window into alternate realities, each one a cosmic laboratory where different versions of physics play out their own evolutionary stories. The little red dots might not be violations of our physical laws, but examples of how matter and energy behave when influenced by the gravitational or quantum effects of nearby universe bubbles. This perspective transforms our sense of cosmic uniqueness and isolation. Instead of being alone in a single vast universe, we might be part of an infinite community of realities, each one contributing its own chapter to an incomprehensibly large story of existence. The mysteries Webb has revealed might be our first direct evidence of this larger tapestry, cosmic postcards from the edges of reality itself. One of the most subtle yet profound aspects of Webb's discoveries involves their relationship to time itself. Not just cosmic time, but the fundamental nature of temporal flow that gives meaning to concepts like cause and effect, past and future, evolution and decay. The objects we've been exploring seem to violate not just our expectations about how quickly things can form and grow, but our deeper assumptions about how time operates on cosmic scales. In our everyday experience, time moves forward in a clear, unambiguous direction. Effects follow causes, entropy increases, and complex structures tend to break down rather than spontaneously assemble. This arrow of time seems so fundamental that we rarely question it, yet it emerges from statistical mechanics rather than being built into the basic laws of physics. At the deepest level, most physical processes are time reversible, meaning they would work just as well running backward as forward. The rapid evolution of early galaxies and the formation of impossibly massive black holes in impossibly short times might be telling us something profound about how time itself behaved in the young universe. Perhaps the arrow of time was less sharp, less unidirectional, allowing for kinds of self-organization and rapid assembly that become impossible, as the universe ages and its statistical properties settle into more familiar patterns. This connects to deeper questions about the nature of cosmic evolution itself. We tend to think of the universe as a story with a clear beginning, middle, and eventual end. But what if time is more complex than this linear narrative suggests? What if the early universe existed in a state where past and future were more fluid, where cause and effect could operate in ways that seem impossible from our current temporal perspective? The little red dots, with their brief existence and mysterious disappearance, might be artifacts of this different kind of temporal flow, objects that could only exist when time itself had properties unlike anything we observe today. Their vanishing from cosmic history might not represent their destruction or evolution into other forms, but their retreat into temporal dimensions we cannot access or observe from our current position in the universe's development. As we approach the conclusion of our journey through these cosmic mysteries, we encounter perhaps the most profound question of all. What role does consciousness play in the universe's apparent drive toward complexity and self-understanding? The fact that the cosmos has evolved minds capable of building instruments like Webb, of detecting and puzzling over these cosmic anomalies, of developing theories about holographic universes and quantum information, suggests that awareness itself might be as fundamental to reality as matter, energy, space, and time. This is not to suggest that consciousness causes cosmic phenomena or that the universe exists only in our minds, but rather to recognize that the emergence of intelligence capable of cosmic contemplation represents something genuinely remarkable in the history of reality. From the quantum vacuum to the formation of atoms, from the birth of stars to the assembly of galaxies, from the chemistry of life to the neuroscience of awareness, the universe seems to be on a trajectory toward understanding itself. The mysterious objects Webb has discovered become part of this larger story of cosmic awakening. Each anomaly we detect, each impossible galaxy or inexplicable black hole, each theoretical breakthrough in our understanding of reality's fundamental nature, contributes to the universe's growing self-awareness. We are not separate observers studying an alien cosmos, but expressions of the cosmos studying itself, temporary arrangements of star stuff that have become capable of wonder, curiosity, and scientific insight. This perspective transforms the meaning of our cosmic detective work. We're not just trying to solve puzzles about distant or participating in the universe's own journey, galaxies and ancient black holes. We toward self-knowledge. Every question we ask, every theory we develop, every moment of awe we experience when contemplating these mysteries becomes part of the cosmos coming to understand its own nature and history. The little red dots and impossible early galaxies are not just objects to be explained, but invitations to expand our conception of what reality might be capable of creating. They challenge us to think more deeply, imagine more broadly, and remain open to possibilities that stretch the boundaries of current understanding. In responding to these challenges, we fulfill part of our role as the universe's way of knowing itself. As Webb continues its patient vigil at the second Lagrange point, collecting ancient photons and revealing new cosmic mysteries with each observation, we stand at the threshold of an unprecedented era of astronomical discovery. The telescope's planned mission duration extends for at least a decade, possibly longer if its systems remain healthy and its fuel reserves last, promising years of continued revelations about the nature of cosmic evolution and the fundamental structure of reality. Future observations will undoubtedly deepen these mysteries, even as they provide new clues toward their resolution. Webb's ability to study the spectra of distant galaxies in unprecedented detail will allow astronomers to probe the chemical composition, physical conditions, and dynamic processes within these enigmatic early objects. Each new spectrum, each additional measurement, each deeper image will add another piece to the cosmic puzzle we've been exploring together. But Webb is not alone in this cosmic detective work. Ground-based telescopes like the extremely large telescope, now under construction in Chile's Atacama Desert, will provide complementary observations with even higher resolution and different wavelength coverage. Space-based missions like the Nancy Grace Roman Space Telescope will survey vast areas of the sky, potentially discovering thousands more of these mysterious early objects and revealing their distribution throughout cosmic history. The theoretical work needed to understand these discoveries is equally exciting. New computer simulations that incorporate quantum mechanics, general relativity, and information theory are beginning to model how the early universe might have operated under conditions very different from those we observe today. These simulations might eventually explain not just how the impossible objects formed, but why they disappeared and what they might tell us about the fundamental nature of space, time, and reality itself. Perhaps most intriguingly, the intersection of astronomical observation with developments in quantum computing and artificial intelligence might open entirely new approaches to understanding these cosmic mysteries. Machine learning algorithms trained on Webb's data might discover patterns and correlations that human astronomers have missed, while quantum computers might eventually simulate the information processing aspects of cosmic evolution in ways that classical computers cannot achieve. As we near the end of our gentle journey through these cosmic mysteries, it's worth pausing to consider what they mean not just for astronomy and physics, but for our understanding of our own place in the grand story of existence. The discoveries we've explored together challenge some of our most basic assumptions about the nature of reality, the flow of time, the relationship between matter and information, and the role of consciousness in cosmic evolution. These are not merely technical questions for specialists to debate in academic journals, but profound inquiries that touch the deepest aspects of human experience and meaning. If the universe is indeed stranger, more complex, and more wonderful than our current theories suggest, then we are part of a reality far more magnificent and mysterious than previous generations could have imagined. The impossible objects Webb has revealed remind us that existence itself is improbable, remarkable, and worthy of our deepest appreciation and wonder. We live in a cosmos that creates black holes so massive they shouldn't exist, galaxies so bright they violate our models of cosmic evolution, and information patterns so complex they might encode the structure of reality itself. And somehow, this same cosmos has also created minds capable of detecting these mysteries, developing theories to explain them, and experiencing awe in contemplating their implications. This connection between the cosmic and the personal, between the larger scales of space and time, and the intimate experience of consciousness and wonder, suggests that our scientific exploration of the universe is also a spiritual journey, a quest to understand not just how reality works, but what it means to be aware, curious, and alive within it. The mysteries remain unsolved, the questions multiply with each new discovery, and the universe continues to surprise us with its creativity and complexity. But perhaps that's exactly as it should be. A cosmos that could be completely understood, fully mapped, and entirely predicted might be less wonderful than one that continues to challenge our assumptions and expand our sense of what's possible. As we drift toward the conclusion of tonight's cosmic meditation, let me leave you with a thought that bridges the scientific and the personal, the cosmic and the intimate. Every atom in your body was forged in the nuclear furnaces of ancient stars, scattered across space when those stars died, and eventually assembled into the complex chemistry that makes your thoughts, dreams, and capacity for wonder possible. You are not separate from the cosmic story we've been exploring. You're part of it. The same quantum processes that might explain the holographic nature of reality operate within the neurons of your brain. The same information patterns that encode the structure of black holes and galaxies also encode your memories, emotions, and sense of identity. The same cosmic evolution that created impossible galaxies in the early universe also created the conditions that allowed life, consciousness, and scientific curiosity to emerge. When you look up at the night sky and feel that sense of awe and mystery, you're experiencing the universe becoming aware of itself. When you ponder these cosmic puzzles and feel your mind stretching to accommodate new possibilities, you're participating in the cosmos's journey towards self-understanding. When you share in the wonder of discovery, you become part of the ongoing story of reality, exploring its own nature. The James Webb Space Telescope will continue its observations, revealing new mysteries and deepening existing ones. Theoretical physicists will continue developing new frameworks for understanding reality's fundamental nature. And each of us, in our own way, will continue to be part of this grand adventure of cosmic discovery and self-understanding. These mysteries remind us that we live in an age of unprecedented discovery, when instruments built by human ingenuity can peer deeper into space and time than ever before, revealing aspects of reality that challenge our most basic assumptions about existence itself. We are privileged to witness this unfolding story of cosmic revelation, to be part of a species that has learned to build time machines disguised as telescopes, and to ask questions that probe the deepest foundations of what it means for anything to exist at all. As you settle into sleep tonight, wherever you are in this vast and wonderful cosmos, carry with you this sense of connection to something infinitely larger and more mysterious than our daily concerns. You are made of star stuff. You are part of the universe's journey towards self-awareness, and you live in an age when the deepest cosmic mysteries are finally beginning to reveal themselves to patient scientific inquiry and boundless human curiosity. The universe is stranger, more beautiful, and more full of surprises than we ever dared imagine. And tomorrow, Webb will collect more ancient light, revealing new chapters in the cosmic story that connects us all. Until we meet again in this quiet corner of cosmic contemplation, sleep well, dream of distant galaxies, and remember that in pondering these mysteries, you participate in the universe's own journey toward understanding itself. And speaking of mysteries that challenge our understanding of reality itself, next time we'll explore one of the most mind-bending discoveries in modern physics. Compelling evidence that our entire three-dimensional universe might actually be a hologram, a projection from information encoded on a two-dimensional surface at the very edges of space and time. Is the universe actually two-dimensional? It's a question that will transform how you think about the nature of existence itself. But perhaps the most profound mystery of all lies not in the objects Webb has discovered, but in the very fabric of space itself, in the invisible force that's been quietly reshaping the cosmos since the universe was barely half its current age. This is dark energy, the enigmatic force that makes up nearly 70% of everything that exists, yet remains as mysterious today as it was when astronomers first stumbled upon its effects 2 decades ago. Picture the universe as a vast balloon being inflated by an unseen hand. For the first several billion years of cosmic history, gravity dominated, pulling galaxies together, slowing the expansion that began with the Big Bang. But then, something changed. Around 5 billion years ago, when our solar system was just beginning to form, this mysterious dark energy began to win the cosmic tug-of-war, accelerating the expansion of space itself. This acceleration isn't like the expansion of gas from an explosion, where material flies outward through pre-existing space. Instead, it's the creation of new space between galaxies, a stretching of the very fabric of reality that carries distant galaxies away from us at ever-increasing speeds. It's as if the universe decided that 5 billion years of gradual decelerating expansion wasn't dramatic enough, and switched to an entirely different mode of cosmic evolution. The implications of this discovery ripple through everything we've been exploring. The little red dots and impossible early galaxies that Webb has revealed existed in a very different universe than the one we inhabit today, not just because they formed when the cosmos was younger and denser, but because they formed in a universe where gravity still dominated, where the rules of cosmic expansion were fundamentally different. Think about it this way. If you were trying to build a sandcastle on a beach where the sand was slowly compacting and settling, you might achieve remarkable architectural feats through patience and careful construction. But if the beach suddenly started expanding rapidly, stretching and pulling apart, those same construction techniques would become impossible. The early universe's ability to create such massive, compact objects might be partly explained by the fact that space itself wasn't yet racing away from itself with today's relentless acceleration. There's something almost melancholic about dark energy's role in cosmic history. Just as the universe was reaching a kind of gravitational maturity, with galaxies settled into their patterns and stellar neighborhoods well established, this mysterious force began pulling everything apart. The little red dots may have vanished not just because they evolved into other forms, but because the expanding space around them made their particular type of compact, efficient structure formation impossible to maintain. Deep within the seemingly empty vacuum of space, something extraordinary is happening that connects to the very foundations of quantum mechanics and might hold clues to understanding both dark energy and the anomalous objects Webb has discovered. Even in the most perfect vacuum where no atoms exist and no classical matter can be found, space itself seethes with activity at the quantum level. Imagine the vacuum as a calm lake surface viewed from a great distance. From far away, the water appears perfectly smooth and still. But as you move closer, you begin to see tiny ripples, waves, and fluctuations that were invisible from afar. At the quantum level, empty space behaves similarly, filled with what physicists call virtual particles, ephemeral pairs of matter and antimatter that spontaneously pop into existence, dance briefly with each other, and then annihilate back into nothingness. These quantum fluctuations aren't just theoretical curiosities, they have measurable effects on the physical world. From the Casimir force that pushes parallel metal plates together in vacuum to the slight shifts in atomic energy levels that can be detected with precision spectroscopy. The vacuum, it turns out, is not empty at all, but alive with a constant background hum of quantum activity. This quantum foam, as it's sometimes called, might be intimately connected to the dark energy that's accelerating cosmic expansion. Some theories suggest that the energy density of quantum vacuum fluctuations could provide the driving force behind the universe's acceleration, though the calculations involved present their own deep mysteries. The theoretical energy density of quantum fluctuations is so enormous that if it all contributed to dark energy, the universe would expand so rapidly that atoms themselves couldn't hold together. The fact that we exist at all suggests that there's some mechanism, some unknown principle of physics that cancels out most of this quantum vacuum energy, leaving behind just a tiny fraction we observe as dark energy. It's as if nature has an incredibly precise accounting system that balances the books of quantum energy to within 1 part in 10 to the 120th power, a level of fine-tuning that makes winning the lottery seem like a certainty. This connects back to our cosmic mysteries in unexpected ways. If the quantum vacuum played a different role in the early universe, if the balance between virtual particle creation and annihilation operated under different rules, when space was younger and denser, it might explain why the little red dots could form with such impossible efficiency, and why early galaxies could grow so much more rapidly than our current theories predict. As we continue our gentle exploration of these interconnected cosmic mysteries, we return to black holes with a new perspective, viewing them not just as gravitational monsters that warp space and time, but as information storage devices of unimaginable capacity. This shift in perspective, from thinking about black holes as destroyers to understanding them as cosmic libraries, represents one of the most profound developments in modern theoretical physics. The key insight came from Stephen Hawking's discovery that black holes have temperature and entropy, properties that seemed impossible for objects from which nothing, not even light, can escape. But if black holes have entropy, they must store information, and the amount of information they can store is proportional not to their volume, as you might expect, but to the area of their event horizon. This leads to a stunning conclusion. A black hole the size of our solar system could store more information than all the books, hard drives, and digital storage devices that have ever existed on Earth, with room left over for the complete quantum state of every atom in 1,000 galaxies. The supermassive black holes at the centres of galaxies, including the impossible ones Webb has discovered in the little red dots, might contain information equivalent to entire universe-sized libraries. But what kind of information? This is where the mystery deepens into something almost mystical. If the holographic principle is correct, if our three-dimensional reality is indeed encoded in information patterns on distant, two-dimensional surfaces, then black holes might be the universe's way of processing and storing the data from which reality itself emerges. Consider the possibility that consciousness, memory, and experience are not produced by neural networks in biological brains, but are aspects of the universe's own information processing capabilities. In this view, the massive black holes Webb has discovered might not just be gravitational anomalies, but cosmic minds of sorts, information processing systems that participate in the universe's journey towards self-awareness. This isn't to anthropomorphize black holes or suggest they think in ways similar to human consciousness, but rather to recognize that information processing, pattern recognition, and complex system behavior might be fundamental features of reality at all scales, from quantum mechanics to cosmology. The strange behaviors of the little red dots and their central black holes might reflect forms of cosmic information processing that we're only beginning to glimpse. There's Anaxagoras and the Greek ancient idea, traced back to Pith philosophers, that the cosmos itself produces music, harmonious vibrations that reflect the mathematical relationships governing celestial motion. While we now know that sound cannot travel through the vacuum of space, modern astronomy has discovered that the universe does indeed sing, just not in ways the ancient philosophers could have imagined. Gravitational waves, ripples in space-time itself caused by the acceleration of massive objects, carry information about cosmic events across billions of light years. When two black holes spiral into each other and merge, they create gravitational wave signatures that can be detected by incredibly sensitive instruments on Earth. These signals, when converted to sound, produce haunting chirps and whoopses that literally are the music of cosmic catastrophe. The supermassive black holes Webb has discovered, with their impossible masses and mysterious behaviours, would have created their own gravitational symphonies during their formation and early evolution. If we could somehow listen to the gravitational waves from the era when little red dots dominated the cosmic landscape, we might hear a very different kind of cosmic music than what we detect today. Imagine the gravitational wave background of the early universe as a cosmic jazz age, filled with rapid-fire improvisations as massive black holes formed, merged, and grew at unprecedented rates. The spacing and rhythm of these gravitational signals might encode information about the physical processes that created these impossible objects, providing clues that complement the light-based observations from telescopes like Webb. Future gravitational wave detectors, planned for deployment in space where they can detect much lower frequency signals, might eventually allow us to listen directly to the formation of the mysterious objects Webb has discovered. We might hear the gravitational songs of the little red dots, the acoustic signatures of impossible galaxy formation, the harmonics of cosmic evolution operating under rules very different from those we observe today. This acoustic archaeology of the early universe represents another frontier in our quest to understand these cosmic mysteries. Just as Webb allows us to see the ancient light from these enigmatic objects, gravitational wave astronomy might allow us to hear their formation, adding an entirely new sensory dimension to our exploration of cosmic history. On the largest scales, the universe reveals a structure of breathtaking beauty and complexity. Galaxies are not scattered randomly through space, but organized into an intricate network called the cosmic web, a vast scaffolding of dark matter filaments that stretches across billions of light years. This cosmic architecture provides the framework within which all the mysterious objects Webb has discovered must be understood. Picture this web as an enormous three-dimensional spider's web, with galaxies strung like dewdrops along invisible filaments of dark matter. At the intersections of these filaments, where multiple threads come together, matter accumulates in dense nodes that become the sites of galaxy clusters. Along the filaments themselves, galaxies form in chains and sheets, following the hidden pathways carved out by dark matter's gravitational influence. The little red dots and impossible early galaxies didn't form in isolation, but within this cosmic web structure, though at a time when the web was much denser and more chaotic than it appears today. In the early universe, the cosmic web was still taking shape, with dark matter filaments colliding, merging, and reconfiguring in ways that created special environments for rapid structure formation. These cosmic web intersections in the early universe might have been like celestial hothouses, regions where the normal processes of galaxy formation were accelerated and amplified by the convergence of multiple dark matter streams. The little red dots might represent fossils of this early phase of cosmic web evolution, objects that formed in the most extreme nodes of the primordial dark matter network. Understanding the cosmic web also helps us appreciate why these mysterious objects disappeared from cosmic history. As the universe expanded and dark energy began to dominate, the cosmic web stretched and thinned. The dense, chaotic intersections that might have enabled rapid galaxy formation gradually gave way to the more stable, predictable structure we observe today. The cosmic web continues to evolve, but at a much more leisurely pace than during the era of the little red dots. Modern galaxies form and grow within well-established filamentary structures, following predictable patterns of accretion and merger. The wild, rapid evolution of the early cosmic web has given way to a more mature, stable architecture that no longer produces the kinds of extreme objects Webb has discovered. Throughout our exploration of these cosmic mysteries, we've encountered a recurring theme that connects the smallest quantum scales to the largest cosmological structures: the universe's apparent drive toward increasing complexity. From the simple hydrogen and helium of the early cosmos to the rich chemistry of planetary systems, from the first primitive galaxies to the intricate structures we observe today, the universe seems to possess an inherent tendency to create increasingly sophisticated arrangements of matter and energy. This arrow of complexity operates alongside the more familiar arrow of time, the thermodynamic principle that entropy tends to increase and systems tend toward disorder. Yet somehow, within pockets of space and time, the universe consistently produces islands of increasing organization, complexity, and information content. From the formation of atoms to the emergence of life, to the development of consciousness capable of contemplating these very processes. The mysterious objects Webb has discovered might represent particularly dramatic examples of this complexification process. Cosmic experiments in rapid organization that push the boundaries of what's possible within the constraints of physics and chemistry. The little red dots, with their impossible black hole masses and compressed stellar populations, might be the universe's attempt to pack maximum complexity into minimum space during an epoch when such extreme organization was possible. This perspective transforms our understanding of these cosmic anomalies from violations of physical law to expressions of the universe's creative potential operating under extreme conditions. Rather than asking why these objects shouldn't exist, we might ask what they reveal about the cosmos's capacity for self-organization, pattern formation, and the generation of novelty within the framework of natural law. The disappearance of these objects from cosmic history might not represent failure or destruction, but graduation to new forms of complexity that we don't yet recognize. Perhaps the little red dots evolved into structures so sophisticated, so far beyond our current understanding, that we can't identify their modern descendants among the galaxies Webb observes today. This connects to deeper questions about the relationship between complexity and consciousness, between the universe's capacity for self-organization and its apparent drive towards self-understanding. The emergence of minds capable of building telescopes, developing theories, and experiencing wonder at cosmic mysteries might be not an accident, but an inevitable consequence of the universe's fundamental tendency toward increasing complexity and self-awareness. As our cosmic meditation draws toward its conclusion, we encounter perhaps the most fundamental mystery of all, the origin of space and time themselves. The objects Webb has discovered, strange as they are, exist within the familiar framework of 3 spatial dimensions and 1 temporal dimension. But what if this framework itself emerged from something more fundamental, something that exists beyond or beneath our normal concepts of space and time? Quantum mechanics suggests that at the smallest scales, the smooth fabric of space-time breaks down into a foam of quantum fluctuations, regions where the very concepts of distance and duration become meaningless. At the Planck scale, roughly 10 to the minus 35 meters, space and time themselves become subject to quantum uncertainty principles, flickering in and out of existence like the virtual particles that populate the quantum vacuum. This quantum foam might hold the key to understanding how the universe itself began and why the early cosmos was capable of producing the impossible objects Webb has revealed. If space and time are emergent properties that crystallized out of more fundamental quantum processes, then the early universe might have existed in a state where the normal rules governing matter, energy, and structure formation were still taking shape. The rapid evolution of early galaxies, the formation of impossibly massive black holes, and the brief existence of little red dots might all be artifacts of this primordial epoch when space and time themselves had different properties than what we observe today. As the universe aged and its space-time structure stabilized, these extreme forms of organization became impossible, locked out by the crystallization of physical law into its current forms. This perspective suggests that the universe's history might be divided into distinct epochs, characterized not just by different temperatures and densities, but by different fundamental structures of reality itself. The era of the little red dots might represent the universe's adolescence, a period when the basic architecture of space-time was still flexible enough to permit forms of organization that seem impossible from our current vantage point. Understanding these quantum origins of space and time requires theories that push far beyond our current knowledge, frameworks that attempt to unify quantum mechanics with general relativity at the most fundamental level. String theory, loop quantum gravity, and other approaches to quantum gravity all suggest that space-time itself might be composed of more basic entities, quantum bits of information that weave together to create the familiar fabric of cosmic experience. As we drift toward the end of our journey through these cosmic mysteries, we encounter ideas that connect modern cosmology to some of humanity's oldest philosophical intuitions about the nature of time, existence, and eternal recurrence. The universe Webb observes is not static, but dynamic, constantly evolving, expanding, and changing its fundamental characteristics as it ages. But what happens in the ultimate future, when dark energy has stretched space so thin that galaxies can no longer see each other, when stars burn out and black holes evaporate, when the universe reaches a state of maximum entropy and minimum organization? Some cosmological models suggest that even then, the story might not be over. Quantum fluctuations in the vacuum might occasionally, over unimaginably vast spans of time, spontaneously create new regions of organized matter and energy. Given infinite time, these fluctuations might eventually produce new universes, new Big Bangs, new opportunities for complexity and consciousness to emerge. The mysterious objects Webb has discovered might be not unique anomalies, but examples of patterns that repeat across cosmic cycles, eternal variations on themes of organization and emergence. This cyclical view of cosmic evolution suggests that the little red dots and impossible early galaxies might not be fossils of a unique historical epoch, but representatives of phenomena that occur whenever the universe is young enough and dense enough to permit such extreme forms of organization. In future cycles, when new universes condense out of quantum foam, similar objects might form again, creating their own versions of cosmic mystery for whatever forms of intelligence evolve to observe them. The idea of eternal return transforms our relationship to these cosmic puzzles. Instead of viewing them as distant historical curiosities, we might see them as eternal possibilities, patterns of organization that represent fundamental capabilities of reality itself. The universe's capacity to create impossible galaxies and mysterious black holes becomes not an accident of early cosmic history, but an expression of the deepest creative potentials built into the structure of existence. This cyclical perspective also provides a kind of cosmic comfort. Even if our own universe eventually reaches a state of maximum entropy and dissolution, the patterns of organization and complexity that produced planets, life, consciousness, and the capacity for wonder might emerge again in future cycles, ensuring that the universe's journey towards self-understanding continues across infinite spans of space and time. Throughout our exploration, we've encountered mathematical relationships and geometric patterns that seem to govern cosmic evolution at every scale, from the quantum realm to the structure of galaxy clusters. These patterns suggest that mathematics is not just a human tool for describing nature, but something more fundamental, perhaps the language in which the universe writes its own story. The golden ratio appears in spiral galaxies and the distribution of seeds in sunflowers. The same exponential functions describe both radioactive decay and cosmic inflation. The mathematical relationships that govern quantum entanglement also appear in the correlations between distant regions of the cosmic microwave background. It's as if the universe operates according to a deep mathematical grammar that connects phenomena across vast differences in scale and complexity. The mysterious objects Webb has discovered might represent particularly elegant expressions of this cosmic mathematics, solutions to cosmic equations that we haven't yet learned to write. The little red dots, with their impossible proportions and brief existence, might be geometric forms that can only exist under specific mathematical conditions that prevailed in the early universe. This mathematical view of reality suggests that the universe's capacity to create impossible objects isn't really impossible at all, but represents the working out of mathematical relationships that transcend our current understanding of physical law. The rapid formation of early galaxies, the growth of supermassive black holes, and the compact organization of little red dots might all be inevitable consequences of cosmic mathematics operating under the extreme conditions of the young universe. Understanding these mathematical patterns might eventually allow us to predict not just what kinds of objects the universe can create, but when and where they will appear. The cosmic web, dark energy, quantum fluctuations, and all the other phenomena we've explored might be expressions of a single, elegant, mathematical structure that describes the universe's evolution from quantum foam to galactic clusters to whatever lies beyond our current observational horizon. As our gentle journey through these cosmic mysteries draws to a close, we find ourselves not with answers, but with a deeper appreciation for the profound questions that connect us to the largest scales of space and time. The objects Webb has discovered remind us that we live in a universe far stranger, more creative, and more wonderful than our ancestors could have imagined, yet also more mysterious than our current theories can fully explain. Each impossible galaxy, each little red dot, each violation of our expectations becomes an invitation to expand our sense of what's possible, to remain humble before the vastness of the unknown, and to maintain the kind of childlike wonder that drives scientific discovery and philosophical inquiry. These cosmic anomalies don't diminish the universe's mystery, they deepen it, revealing layers of complexity and beauty that we're only beginning to glimpse. The fact that these objects challenge our understanding is not a failure of science, but a testament to the universe's inexhaustible capacity for surprise and revelation. Every answer we discover opens new questions. Every mystery we solve reveals deeper puzzles. Every boundary we cross shows us new horizons to explore. This is the essence of cosmic discovery, the endless journey into a universe that will always be larger, stranger, and more wonderful than our current ability to comprehend it. And perhaps that's exactly as it should be. A cosmos that could be completely mapped, fully understood, and entirely predicted might be less magnificent than one that continues to challenge our assumptions, stretch our imaginations, and invite us deeper into the mystery of existence itself. The universe Webb has revealed to us is not a solved puzzle, but an ongoing revelation. Not a finished story, but an ever-unfolding narrative of cosmic creativity and complexity. As you carry these ideas with you into your daily life, remember that you are not separate from this cosmic story, but intimately connected to it. The atoms in your body were forged in the nuclear furnaces of ancient stars. The oxygen you breathe was created in stellar explosions. The carbon in your DNA was scattered across space when massive stars died and was eventually incorporated into the chemistry that makes your thoughts and dreams possible. You are a temporary arrangement of star stuff that has become capable of wonder, consciousness, and scientific curiosity. When you contemplate these cosmic mysteries, you participate in the universe's own journey towards self-understanding. When you feel awe at the beauty and strangeness of existence, you become part of the cosmos, awakening to its own magnificent complexity. The James Webb Space Telescope will continue its observations, revealing new chapters in this ongoing story of cosmic discovery. Theoretical physicists will continue developing new frameworks for understanding reality's deepest structures, and each of us, in our own way, will continue to be part of this grand adventure of exploration and understanding that connects us to the largest and smallest scales of existence. Sleep well tonight, knowing that you live in an age of unprecedented discovery, when human ingenuity has created instruments capable of peering deeper into the mysteries of space and time than ever before. Dream of distant galaxies, impossible black holes, and the endless creativity of a universe that continues to surprise and delight us with its capacity for beauty, complexity, and wonder. And remember, tomorrow Webb will collect more ancient light, revealing new aspects of the cosmic story that includes us all. Until we meet again in this quiet corner of scientific contemplation, carry with you this sense of connection to something infinitely larger and more mysterious than our everyday concerns. You are part of the universe's journey toward understanding itself, and that makes your curiosity, your wonder, and your capacity for awe not just personal experiences, but cosmic events of genuine significance. Speaking of cosmic mysteries that challenge everything we think we know about reality itself, next time we'll explore one of the most mind-bending possibilities in modern physics: compelling evidence that our entire three-dimensional universe might actually be a hologram, a projection of information encoded on a two-dimensional surface, at the very edges of space and time. Is the universe actually two-dimensional? It's a question that will fundamentally transform how you understand the nature of existence, consciousness, and your place in the cosmic order. As we continue drifting through this cosmic meditation, let's pause for a moment to appreciate something quite remarkable about our current moment in the universe's long history. We exist at a time when technology has finally caught up with human curiosity, when our instruments can peer across billions of years of cosmic time and reveal secrets that would have seemed like pure magic to astronomers just a generation ago. Webb's position at the second Lagrange point isn't just a convenient parking spot in space. It's a carefully chosen vantage point that allows the telescope to observe the universe with unprecedented clarity and patience. Imagine sitting in perfect stillness while the cosmos slowly rotates around you, revealing its deepest secrets, one ancient photon at a time. This is essentially what Webb does, day after day, night after night, collecting the whispered stories of distant galaxies and impossible objects with the dedication of a cosmic librarian preserving the universe's most precious manuscripts. The telescope's instruments work together like a symphony orchestra of scientific precision. Its near-infrared camera captures images of unprecedented sharpness, revealing details in distant galaxies that were invisible to previous generations of telescopes. The near-infrared spectrograph splits starlight into its component colours, allowing astronomers to read the chemical signatures of objects billions of light-years away. The mid-infrared instrument peers through cosmic dust that would otherwise obscure our view, while the fine guidance sensor keeps everything precisely aligned as Webb tracks its targets across the sky. But perhaps the most remarkable aspect of Webb's observations isn't just what it sees, but how it sees. Every image the telescope captures is essentially a time machine photograph, showing us not just where distant objects are, but when they were. The light from the little red dots we've been exploring has been travelling toward us for over 13 billion years, carrying within its patterns the story of how these mysterious objects looked when the universe was young and strange and governed by rules we're still trying to understand. This temporal archaeology allows us to watch cosmic evolution in action, to see how the universe has changed and grown over the vast spans of deep time. It's like having access to a cosmic photo album that spans nearly the entire history of everything, from the first galaxies to form after the cosmic dark ages, to the mature galactic systems we observe in our local cosmic neighbourhood today. In the quiet halls of theoretical physics departments around the world, something beautiful is happening. Researchers are taking Webb's impossible discoveries and weaving them into new mathematical frameworks, creating theoretical tapestries that attempt to explain how the universe could create objects that seem to violate everything we thought we knew about cosmic evolution. This is how science progresses at its most elegant, through the delicate dance between observation and theory, between what we see and what we can imagine. Each mysterious object Webb discovers becomes a puzzle piece that theorists must fit into the larger picture of cosmic understanding, sometimes requiring them to completely redesign the puzzle itself. Consider the theoretical challenge posed by the little red dots. How do you explain galaxies that contain black holes weighing nearly half as much as all their stars combined? The mathematical models that describe galaxy formation have been refined over decades, tested against thousands of observations, and verified through countless computer simulations. Yet these tiny red objects seem to mock such careful theoretical construction. Some researchers have proposed that the early universe operated under conditions so extreme that our normal scaling relationships simply didn't apply. Perhaps when space was denser and more chaotic, when the cosmic web was still taking shape through violent collisions and rapid mergers, the usual bottlenecks that prevent rapid black hole growth were temporarily suspended. Others suggest that we're witnessing the aftermath of primordial black holes, objects that formed not through stellar collapse but through the direct gravitational collapse of dense regions in the early universe. These primordial seeds could have grown through mechanisms that don't exist in today's cosmos, accumulating mass at rates that seem impossible by modern standards. Still, other theorists have proposed that the little red dots represent a completely unknown phase of cosmic evolution, a brief but crucial period when the universe's fundamental properties allowed for forms of organization that can no longer occur. It's as if the cosmos went through an adolescent phase, a time of rapid growth and experimentation that ended when the universe matured into its current, more stable configuration. Each theoretical framework brings its own predictions and implications, creating a rich landscape of ideas that will guide future observations and inspire new ways of thinking about cosmic evolution. This is the beauty of the scientific process, how mystery becomes the mother of understanding, how confusion becomes the catalyst for breakthrough. Webb's discoveries don't exist in isolation, but send ripples throughout our understanding of physics, astronomy, and our place in the cosmic order. Each impossible object, each violation of our expectations, forces us to reconsider not just how the universe works, but how we think about the relationship between theory and reality. Take the rapid pace of early galaxy formation that Webb has revealed. If massive, mature galaxies could assemble in just a few 100 million years after the Big Bang, what does this tell us about the efficiency of star formation in the early universe? How does it change our understanding of when the first heavy elements were created and dispersed throughout space? When did the universe become chemically rich enough to support the formation of planets and potentially life? These questions cascade through multiple fields of study. Cosmologists must reconsider their models of structure formation. Stellar astronomers need to rethink their understanding of how the first stars lived and died. Astrobiologists wonder whether life could have emerged much earlier in cosmic history than previously thought possible. The discoveries also have profound implications for our understanding of dark matter and dark energy. If galaxies could form more rapidly and grow more massive than our models predict, perhaps dark matter behaves differently than we assumed, or perhaps its distribution in the early universe was more complex and varied than current theories suggest. Even our understanding of fundamental physics might need revision. The extreme conditions that allowed the little red dots to form might reveal new aspects of general relativity, quantum mechanics, or the mysterious interface between these two foundational theories of modern physics. This is how scientific revolutions begin, not with dramatic announcements or sudden revelations, but with quiet accumulations of observations that slowly but persistently refuse to fit into existing theoretical frameworks. Webb's discoveries are still too new, too fresh for us to fully understand their implications, but they're already beginning to reshape how we think about the universe's capacity for surprise and creativity. The mysteries remain unsolved, the questions multiply with each new discovery, and the universe continues to surprise us with its endless capacity for wonder and revelation. As Webb keeps its patient vigil in the darkness of space, collecting ancient photons that have travelled across billions of years to reach us, we're reminded that we live in an extraordinary moment in cosmic history, when human curiosity has finally created instruments capable of peering into the deeper secrets of existence itself. These impossible galaxies and mysterious little red dots aren't just distant objects to be catalogued and explained. They're invitations to expand our imagination, to remain humble before the vastness of the unknown, and to continue participating in the universe's own beautiful journey toward understanding itself.